Swayam Prabha. Digital India. Educated India.
Hello and welcome back once again to this lecture series on aluminum based alloys and metal matrix composites. Okay, so right now we are talking about this grain refinement by melt inoculation, which is basically heterogeneous nucleation in the liquid metal. And this heterogeneous nucleation surface is provided by the inoculant, which is added to the liquid metal in the form of some solid particles. Okay, and we have talked about the different kinds of inoculants or grain refiners which are generally used in aluminium and its alloys. So here are those elements which are used as inoculant or grain refiners for aluminium alloys. So these are basically added as aluminium master alloys, and out of all these, titanium has been found to be most effective. And as I said, this is added as aluminium titanium master alloy, which will provide these aluminide particles which will act as the heterogeneous surface for the nucleation to occur. Okay, so on these particles, the alpha aluminium will form from the liquid metal as you cool it below the liquidus temperature. Okay, and many times a third element is also added. For example, in this kind of aluminium titanium boron master alloys, the ternary master alloys that you have, this will also provide you an additional nucleating surface in the form of TiB2 particles. Okay, and then we talked about the concentrations of such grain refiners which is needed for the grain refinement, and we have seen that these are added in very minor quantities like 0.01% to 0.05% in that range. Okay, and then we talked about the different parameters which affect the grain refinement efficiency. So apart from the titanium to boron ratio in case of the aluminium titanium boron master alloys, you also have the reaction temperature and time as the main process parameters. Okay, and these process parameters also affect the morphology of the particles, and we have seen that the morphology also plays an important role in the grain refinement process. Okay, so depending on the morphology of the particles, the grain refinement efficiency can vary, and we have seen that a morphology which can provide a number of facets or a faceted kind of morphology for these aluminide particles is good for better grain refinement or higher grain refinement efficiency. Okay, because this kind of faceted particles can provide some planes which have low dysregistry or low mismatch with the planes of aluminium, because this kind of planes have some orientation relationship with the aluminium crystals which are forming, and therefore aluminium can easily nucleate on such planes, right? And that is how the morphology comes into picture over here in terms of these planes, which can provide a surface of low dysregistry for the aluminium to nucleate. Okay, so these are the things that we discussed in the previous class. So today we are going to look at the mechanisms through which the nucleation occurs on such heterogeneous surfaces. So there are a number of mechanisms proposed to explain the grain refinement process which occurs through the addition of such inoculant or grain refiners, and one of them goes by the name carbide boride theory. So this is one of the theories proposed to explain the mechanism of grain refinement in melt inoculation. So this basically says, as the name suggests, that some carbide particles can form in presence of titanium in the liquid metal, and those will act as the heterogeneous nucleation surface. So if you have titanium, then titanium carbide will form even without the addition of carbon externally. So carbon, which may be present in very small amount in the range of several hundreds of ppm, is enough for formation of such titanium carbide particles. Right, so even without external addition of carbon, these TIC particles can form, and they will act as the heterogeneous nucleation surface. And if you have boron, then of course you will have the boride particles forming into the melt. So borides such as aluminium boride, titanium boride, or a complex boride like aluminium titanium boride can form in the liquid metal as you add these grain refiners, and this will lead to heterogeneous nucleation, right? Now, if you look at this particular surface, TiB2, because that is one thing which is very common in aluminium alloys, presence of these TiB2 particles. First of all, it should provide a surface on which aluminium can easily nucleate, in the sense that it should be a surface which can lead to easy wetting by the aluminium which is forming on such surfaces. Okay, so the aluminium should be able to wet the surface, and this would depend on the contact angle. A lower contact angle is always good for wetting, and we have seen that the contact angle depends on the surface energies. So if you consider the heterogeneous nucleation, we can go back to this diagram once again. So this is the particle surface on which the solid aluminium is forming. Okay, so we can call that as surface P. P stands for the particle. So this is the solid particle interfacial energy that you have, because this is the solid over here, and this one is the liquid particle interfacial energy. And here of course you have the solid liquid interfacial energy, and this is the contact angle. Okay. So from here you can see that it depends on gamma LP and the other two surface energies through this particular relationship, which comes from the balance of forces. So from here you can see that a low gamma LP is not good for weighting. And therefore a particle surface which provides a low gamma LP will not act as a good nucleating surface. Okay, so in case of TiB2, this gamma LP is low. And therefore TiB2 alone is not a good nucleant. And the other factor which goes against TiB2 in terms of its grain refinement efficiency is the fact that it does not have any plane which can provide a low disk registry with aluminium or low mismatch with aluminium. So here the TiB2 planes will have a higher mismatch. With aluminium. Okay. For example, if you compare this disk registry or the mismatch with a boride particle such as aluminium boride, you will see that this kind of borides will have planes like this 0, 0, 0, 1. Having some orientation relationship with 1, 1, 1 planes of aluminium, and the disk registry is low. This is around 5.2% for aluminium boride particles. But for TiB2, if you see the disk registry, then it is more than aluminium boride, standing at 5.9%. Okay. But aluminium boride, on the other hand, is not stable. It is less stable compared to TiB2. So when you have added boron, it is more likely that TiB2 particles will be present and not AlB2. Okay. So therefore, because of such issues with TiB2, it is not added alone, rather it is combined with titanium and added in the form of these ternary master alloys, so that you can also have the presence of Al3Ti particles, which are much more effective in terms of nucleating the aluminium. Okay. And this is because of the fact that this kind of Al3Ti particles can provide planes which have low disk registry with aluminium, and as a result of that, aluminium can easily nucleate on such surfaces. So now coming back to these mechanisms, first one we have seen, that is the carbide-boride theory, which says that carbide or boride particles are present depending on whether you have carbon or boron coming in contact with the titanium, and these particles will act as the heterogeneous surface. The next theory with regard to this grain refinement by melt inoculant is the peritectic theory. So this theory says that there is a peritectic reaction between liquid and the Al3Ti. So therefore these Al3Ti particles nucleate aluminium through a peritectic reaction, which is as follows. This reaction occurs at 0.15% titanium. If you look at the phase diagram of aluminium titanium, and 665 degrees Celsius temperature. So this alpha aluminium, which is formed through this peritectic reaction, now actually can act as the heterogeneous nucleating surface for the actual aluminium to form when you cool it below the liquidus temperature, right? Because if you talk about pure aluminium, it the solidification starts at around 660 degrees Celsius, right? But this peritectic reaction occurs at 665 degrees Celsius. So even before the aluminium solid phase starts to form from the liquid phase, you already have this alpha aluminium phase present in the liquid, and now this will act as the nucleating surface, right? So that's what I meant when I say that it nucleates aluminium through a peritectic reaction, right? So that is basically through this alpha aluminium which forms due to the peritectic reaction, okay? Just to clarify this 660 degrees Celsius, let me elaborate a bit more. See, if you talk about, let's say, pure aluminium, the melting point is around 660, right? The equilibrium melting point. So when you talk about the solidification of aluminium as such, it will start forming 660 degrees Celsius and below, right? It will start forming when the temperature reaches 660 degrees Celsius, isn't it? But what I am saying here, the peritectic reaction occurs above that. It occurs at 665 degrees Celsius. That means this alpha aluminium which forms due to this peritectic reaction is actually stable in the liquid, in liquid aluminium, right? And that is why it will be able to act as the nucleating surface for this pure aluminium, which will form at 660 degrees Celsius, right? So it is not really through the Al3Ti which will act as the nucleating surface, but rather it will act indirectly by first nucleating this peritectic phase, alpha aluminium, through the peritectic reaction, which in turn will act as the heterogeneous nucleating surface instead of Al3Ti itself acting as the heterogeneous surface. Yeah, so that is why the theory goes by the name peritectic theory, because it says this peritectic alpha aluminium which forms, that actually acts as the heterogeneous surface. But there are some limitations of this theory, particularly with regard to the composition, if you see, at which the peritectic reaction occurs. It occurs, I said before, at 0.15% titanium, right? If you look at the aluminium titanium phase diagram, you would find this peritectic at 0.15% titanium at a temperature of 665 degrees Celsius. But titanium addition is done in very small amounts, as we have discussed before, in the range of 0.01%. Right, so it is too low for the peritectic reaction to occur, right? But still people say it can occur, and some research has suggested that boron can actually influence the peritectic reaction and it can cause a shift in the peritectic composition. And others suggest that a ternary eutectic is also possible at 659.5 degrees Celsius. And in terms of composition, it is at 0.05% titanium and 0.01% boron. And the ternary eutectic reaction goes as follows. And some have also suggested presence of a ternary quasi-peritectic. At around 0.0001% boron and 0.15% titanium. And this quasi-peritectic goes as follows. Right, so these are the different ways by which the heterogeneous surface can be generated, and different theories are proposed to explain that, right? So it could be a simple peritectic reaction, it could be a eutectic, a ternary eutectic, or it could be also a quasi-peritectic, right? So all these reactions will lead to the heterogeneous surface, which will nucleate the aluminium. And Al3Ti, we can see it is always there because, as we have discussed before, it has a low this registry with aluminium. For TiB2 we have seen it was around 5.9%. But for Al3Ti particles it is much lower, around 4%. Okay, and this planes of 112 planes of Al3Ti exhibit low lattice mismatch with 1 planes of aluminium. Right, so this is the other theory for this heterogeneous nucleation that occurs in aluminium when a grain refiner is added. Okay, so this is through the occurrence of a peritectic reaction, and there are suggestions that other kind of reactions such as a ternary eutectic or a quasi-peritectic can also occur depending on the composition of the nucleant which is added to the molten metal. So with that we come to the end of this lecture. Thank you for watching.